All right, so today I want to talk about this paper and multidimensional concept discovery, MCD, a unifying framework with completeness guarantees. Came out 2 years ago, and it's relatively well cited in the literature. And I wanted to just review it. Pardon all the gibberish here. I was just testing some stuff. Okay, so let's dive into it. I've already annotated this. So this approach is pretty nice, and they do something pretty nice, and we can talk about the method. And then I have some issues, I guess, with the experiments that we'll get into. And we can talk about maybe where some of the weaknesses are and what some things to do in the future. So some of the big differentiations about this work is that they introduce completeness guarantees within the context of concept-based explanations. So completeness guarantee is very common in something like SHAP or other types of feature attribution works, but not as common in concept-based explainability. And one of the first things that they do to achieve this is they introduce the idea of representing concepts as multidimensional subspaces. And so typically, they have this really nice figure here. So typically we'll think of concepts, we'll look at the intermediate representations of a network in any layer. And, we'll look at those concepts and we'll think of them as these vectors in that space. And then, different methods will allow different relaxations of constraints, right? So, in D1, you just kind of look at each of the features or the neurons, right, as the concepts, or like in the case of CNNs, the filters as the concepts, and then you can kind of expand, right? In D2, you look at orthogonal directions. This is like if you do something like PCA, right? You'll get these orthogonal directions. And then future works relax this orthogonality constraint, right? You can do something like non-negative matrix factorization, and you can get these arbitrary directions. To an extent, also sparse autoencoders will give you these arbitrary directions, right, as concepts. And then what they do in this work, right, is instead of thinking of concepts being represented as a single vector, right, a 1D vector, they look at concepts as subspaces, right, of any arbitrary dimensionality. That also includes, right, all of the ones before, right, but you can also get hyperplanes, right, and the key here is that it's linear. So this is what they do, and they argue this is the most general approach, and this will lead to faithful concepts that kind of help satisfy the completeness guarantee. So, to make all of these, to make all their arguments in this paper, they make this assumption repeatedly that they're going to basically assume that on top of these features that we're considering, there's just linear operations, right? So average pooling and a linear classification head. Okay, and you'll see this theme kind of repeated throughout the paper, and we'll touch on it at the end. So this is the first main contribution, is the multidimensional subspaces. And they argue that multidimensional subspaces ensure concise explanations. So, if you have a concept that's like 10-dimensional, right, D3 like would have captured that same concept using 10 separate concepts, right? And so in this way, they argue that you can get much broader concepts that cover more of the model's kind of reasoning, right? But you don't need as many, right? So you can get away with like 3 or 4 or something like that, right? As opposed to having so many of these single dimensional concepts, these vector concepts. So that's their argument. And then, the last thing they do is the completeness. And again, to achieve completeness, they're going to restrict to a high level feature layer, right? Only succeeded by linear operations. And then, with this, they'll be able to tease out this completeness relation. And, this is something that's often missing from concept-based explanations, which is a really nice property to have. And, what is completeness? Just as an aside. So there's local completeness. Maybe I'll do it in black, where it's like the models let's say like for a given class, right? Like let's say for the dog, your model gave you a logit score, right? Before the softmax, a logit score of like 4, right? So then you can decompose this into the concepts, right? And it'll give you, so like let's say you discovered different concepts, C2, let's just say you discovered 3 concepts, right? Maybe you somehow are able to decompose this into like 1.5, -2, and then 4.5, right? And so you can say like adding all of these together, right, gives you the original logit score, right? And so this is what we refer to as completeness. That the final prediction is expressible as a linear combination of your kind of concept attributions in this case, right? In the typical literature, you'll do feature attributions, right? So like I don't think I need to give an example. And then, you can also talk about completeness in the aspect of global completeness, which very often is like if my model is like 60, let's just do it for giggles, 69% accurate, right? I can say what the effect is of C1, C2, and C3 for this accuracy, right? So maybe C3 is like giving me 15% accuracy, and then, right, like this. So that's kind of how what completeness means. And so, we don't have that for concept-based explanations, and it's a nice property to have for sure, because it makes it much more interpretable, right, much more understandable what the impact of each of these concepts are. Okay, great. Okay, so that's kind of all the great things about this method, and let's talk about what the method actually does. Okay, so the first thing is defining out what the concept actually is, what a concept actually is. And we've already touched on this, but some of the mechanics here might be helpful. So you're going to split your model into 2 parts. This is very common in concept-based literature, right? You're going to have part A, which goes from input to some embeddings or representation, right? Which they're calling H here, and then prediction mapping G, which takes you from the embeddings all the way to the prediction. Okay. Oops, sorry. We're gonna find concepts kind of on these embeddings here, okay, on these representations here, and so what they say. So in general, because we're operating in vision, you're gonna get representations that have some spatial dimensionality, right? H and W are your spatial dimensionality, and F is like the number of channels you have. So like in the ResNet, right, this is like commonly something like this, I think, or maybe who knows what this last dimension is. It always changes depending on the model you're using. But the 7x7 is the spatial dimensionality, and then you have these features that are 2048 dimensional. So what they do is spatially deconstruct the feature maps to obtain these feature vectors, right? So like you're gonna have these feature maps, right? This is like, in this case, it's 2x2 times F, right? So they have some depth here, right? So they're gonna spatially deconstruct this. So you can just think of it as almost like flattening. I'm gonna just flatten this, right? And like look at each of these vector. This is like a vector, right? This is a F dimensional vector. I'm gonna look at these vectors all kind of individually, right? As like points, right? In an F dimensional feature space, right? So all of these are kind of get mapped onto, if this is my F dimensional feature space, right, they'll all get mapped onto like points, right? Why did that happen? They'll all get mapped onto points, right, in this feature space. Oh my God. Maybe I can turn off that setting somehow. They'll get mapped onto points in this feature space. So that's all that means. Yeah, so then, a concept is a d-dimensional linear subspace. So it's just a span of vectors, and the nice thing here is that the dimensionality DL is arbitrary. Not arbitrary, but it can vary. So, it's much more general than previous methods where this was always just one dimension, right? Your concept was just a single vector. Okay, and same argument they're making here, right? However, for a last linear layer that is only followed by a linear classification head, right, which we specialize to, so they're kind of restricting their work to this case, which is fine. Okay, so how do you actually find these? We talked about how the concepts are defined. How do you actually find them? So there's 2 steps. You're going to cluster feature vectors, and then you're going to find a basis after that. And I think it's just easiest from the picture to understand it. So like you're gonna have a collection of points, right? This is like the collection of points I drew here, right? You're just gonna have, you put some images in. I'll just show you here. You put some images into your model, right? You put some images into your model, you're gonna get these points, right? Now in your feature grid, right? In your feature grid, each of these is a vector, right? And each of these kind of belongs to a, you can kind of plot it, right? And in this dimensional space. And so what you're gonna do is first you're gonna cluster and decide which points belong together. So you can see here they've already done that, right? They've done the clustering. These points belong in one cluster, these points belong in another cluster, etc. And the actual algorithm doesn't matter. They talk about some motivation for the algorithm they use, but that's kind of a detail that's not really super pertinent for us. And then once you have the points in a cluster, right, for each cluster, you're only gonna take these points and you're gonna run PCA on it, okay? And the idea behind running PCA is that you can find the basis, right? So like they're gonna do two things first. First, they're gonna estimate what is the dimensionality, and they talk about using some heuristic, which doesn't really matter. So let's just say like the dimensionality of this space is 3 that they estimate out of these points. Then you can run PCA on these points and just keep the top 3 components, right, that you get from PCA, and that'll span your basis. At least with the minimum reconstruction error, it'll span the basis, right, of these points. So that's how they that's how they find the concept. And you know, this basis will define out the hyperplane, right? So like this defines out a hyperplane, right, in the space. And you know, the number of components you have in your basis, that's the dimensionality of your hyperspace, of your hyperplane. Okay, so that's basically what they do. I don't think there's any, yeah, we just talked about all of that. So yeah, just some notation here, just so that you don't get lost in the notation. The capital C are the clusters of points, right? And then for each cluster, you're going to determine its dimensionality, DL. Remember, L is keeping the, like, what cluster number it is, right? For the Lth cluster. And then you're going to find these basis vectors C, L, J. Okay, so the C, J, L actually define out the hyperplane for subspace CL. Okay, so that's just the notation. Okay, so the next parts are like now you have your concepts. What do you do? Okay, so first thing they do is they recognize, hey, the concepts that we have may not be fully representative of what the model is doing, and we're going to define out the orthogonal complement, right, of the subspace span by all concepts. Okay, so this is all concepts. So like, I just draw a shitty version in 2D, but like, let's just say somehow all of your concepts are like in this. Oh, that's a cool color. Oh, huh. Well, let's not get so fancy. Let's just say all your concepts are in this direction here, right? So then obviously the orthogonal complement is going to be here, right, of the space. So that's what they're basically doing, is that they're going to define out the orthogonal complement. So I guess like another way to think about it is like, let's just say your F dimension is like 2048, right? And the rank of the span of all your C1 to, what are they saying? C and C, which is the number of concepts. Let's just say this is equal to some number, right? Let's just say it's equal to like 500 or whatever, right? So then you're going to be able to define out an orthogonal complement that just, you know, is everything else that's not in this, right? It's all parts of F that are not in this, that are not captured by the concepts, right? So the rank here will be, let's just do some quick maths. Make sense? Hope it does. Okay. Yeah, and the main reason they're doing this is just to ensure that the union of all concepts spans the entire feature space, because they want to say something about completeness, right? So to say that, you have to make sure that you're not missing out, that you're fully capturing the model. Okay, so they're going to talk about two things. We'll go by them step by step. First, they're going to talk about concept activation maps, which is basically answering the question, is the concept present, what I put here in blue? So what it does in words is quantify the activation, okay, of a given concept from a certain spatial location for a given sample. It's just like a bunch of words, but I think it's best done with an example. So like, let's just say you have an input sample, right? And this is like the feature map you get out, right? Let's just say, for example, it is 2 cross 2 cross, let's just say 2048, okay? Or yeah, let's just say 2048. So like each of these, as we talked about before, each of these is a vector, right? And you can kind of plot it. And in this f-dimensional space, and here I'm just visualizing two components because, we're humans. And let's just say that these two components are the concepts, right? Let's just say that they exactly align, and these are the concepts. So what they're saying, what the authors are saying is that we'll kind of project all the point onto the concept space, right? Which is what I'm doing here. And then, for any given concept, like for F1, right, you can find this concept activation map. So like F1 for this blue point is -4, right? And for this green point here, is -2, right? So this concept spatially, right, in the top left, it's -4, and then in the bottom right, it's -2. Oh, what happened? My mistake. So this is how you can get, man, I hate when that happens. Okay, so this is how you can kind of get a concept activation map for a given concept. Okay, you just see like how much it's active for all the vectors that you have, right? Like in your spatial feature map. Okay, yeah, and then they introduce this idea of concept prototypes. It's a pretty old idea in this literature, but the way they operationalize it is you want to choose your input samples to come up with prototypes for some concept F1, right? For some concept F1 to come up with these prototypes, you're going to choose your input samples B such that the concept is maximally activated, right? At one of these points. So maybe like the max for this B is -2, which means it's not really that activated, right? But for like another B, the max is like 10, right? Which means like, oh shit, it's really activated, which means the concept is probably present in this image. And so this image is a prototype of that concept. So that's all they mean. Then, they kind of hedge a little bit. They want to say that their method is applicable, but in general, like the idea of concept activation maps is only really valid if locations in your feature map, right, align with the input space, right? So like in CNNs, right, I know like the feature in this location looked at the top left of my image, right? So like if this was my image, right, it looked at like the kind of top left. Oh my god. I wonder how I can turn that off. It looked at like, maybe I put it in red. It looked at the top left, right, of this image. So that's what they mean. And for transformers, you don't have like such guarantees, although like kind of, I guess, empirically we've kind of seen it. So that's all they're trying to say. Okay, so the second thing is the concept relevant heat maps. And this is really just trying to tell you what the impact of the concept is on the model. So it's like one thing for the model to identify if a concept is there. And it's another thing for that concept to like have some impact, right, on the model's prediction. Like just because I found the sky, right, just because I found a concept of the sky doesn't necessarily tell me anything about if there's a human, right? Or maybe it does. And so we're just trying to understand what concepts the model relies on for its prediction. So again, this is their hedging. We specialize to the last hidden layer, which, it's kind of a strong constraint, but it's reasonable. It's a reasonable starting point. This type of stuff is a little difficult, and so it's fine. And, it's relatively simple what we do. You just, we decompose the feature vectors up here. Maybe I should have talked about the math. It doesn't really matter. This is kind of what I just showed in the image, right? Is you have a feature vector phi, right, which is like this right here, the feature vector phi, and then you can decompose it into these contributions for every L, for every concept L. So it's the same thing here, right? When you have phi, I already know phi L times W, right? And so I can just say like, I can come up with this value RL, which is the local concept relevance. And so you're just taking like dot products essentially. And the W just, I guess I didn't introduce it, but the W is the weight vector. And the weight vector will operate on the embedding space, right? So if this is my embedding space here, I'll have like a weight vector, right? That like operates on this embedding space, and I'll be taking dot products, and that weight vector will give me a score for this class, right? Maybe this is like dog, and then I have another weight vector here for like cat or something, right? So that's all they're saying. And in the same way, you can get a heat map, right? So you can apply it on phi. If your model is doing average pooling, you can apply it after the average pooling to just understand the logits, right? So the class logit under consideration, is what they're saying here. And then you can also do it to the feature vectors before pooling, and this will give you the relevance heat map. Yeah, this will give you the relevance. This will give you a heat map. And they're the same. They say it here. It reduces to the other one like after spatial pooling, right? So it's not anything super fancy. Okay, so the last thing is the global relevance and completeness score. So like above here, this is local relevance, like what we just talked about is like local. And to do it globally, you just decompose the weight vector itself. So you don't look at the feature vector because obviously the feature vector is specific to the sample. So you just decompose the weight vector itself. And then they have some fancy math here. So these summations in general go to NC plus 1. So NC is the number of concepts, okay? And then it's plus 1 because you're adding the orthogonal complement, right? So basically what they're saying here is that the norm of W, right, equals the complement plus like the norm of all the other W's. And you can do this because they're independent linearly, right? And so like it's just a little property, you can derive it for yourself, right? But if you just have two vectors or like two sets or whatever, you get this A component and B, and then these components here will equal 0 because they're independent, or they're orthogonal, whatever you want to call it. And then you can do some more math here and expand it out. And this is right here, just the cosine similarity, right? So just to walk through that math really quickly here, like you can do the same thing above, like with 3 components, right? If you have 3 vectors, and obviously you'll get the norm part, right? And then over here you'll get like the pairwise dot products, right? You'll get the pairwise dot products, and you can also express this as they do in terms of cosine similarity. And so that's how you get this relationship here. L is not equal to K, because if L was equal to K, L is not equal to K, because if L is equal to K, then it's just it's just this term here. Okay. So that's how you do the math. I kind of glossed over it, so hopefully it's not confusing. Okay, so the idea is that we can use this to help us decompose what a completeness score is. And so what they do is that you take out the orthogonal complement, right, from 1. so you do 1 minus the proportion of the magnitude, right? That's captured by the orthogonal complement. So 1 minus the proportion of W, right? That's captured by this orthogonal complement. And that tells you like how much your concepts are explaining, right? So if the orthogonal complement is like only 10%, right? Like if this quantity is only 10%, then I know my completeness of the concept is covering 90% of W, meaning like I can recover 90% of the magnitude, right, of W from my concepts. So that is what they say here in words. It's the fraction of W which is explained by all concepts. And obviously this is for a given class. So then they say some weird stuff here. I don't really know what the point of this, but they're just saying that you can lower and upper bound the magnitude of W, but I don't really understand, what the use of all of that is. So I don't think I need to burden you with any of that. Okay, so some alternative variants. So you can replace the clustering, so you can discover concepts with any number of ways. You can discover concepts by doing k-means, right? They introduced a specific method called SSC, which is sparse subspace clustering. It's its own, I guess, field in its own right, or area of research in its own right. But instead of doing that, you can do k-means. And if you're going to do k-means, you would use k-means in a very similar way, where k-means is used to cluster the features, and then you can use PCA to find those subspaces. But obviously, one of the downsides is that it's not clear that, it's not clear that these features here like would fit well on a linear manifold, right? Or on like a linear subspace. So that's like one reason why k-means might not be as good. And then, you can just use vanilla PCA, and this is similar to a previously published technique called ICE. So they experiment with that in their experimental section. Okay, this last part is a little interesting. So in general, you can find two different subspaces with their method, and the subspaces do not need to be orthogonal. That's not a constraint that they have. But we can kind of enforce that using like some type of greedy algorithm, right? So the idea is you're going to iteratively, in an iterative fashion, we're going to construct these orthogonal subspaces. Okay, so first you're going to start with this empty set here, and then you're gonna add the subspace, the concept subspace, that leads to the largest increase in the completeness score. Okay, so it captures most of the W basically. And then iteratively you're gonna add other subspaces and you're gonna select the one that leads to the largest completeness score, except you're gonna modify that subspace by basically removing whatever part lies in the span of the selected set, right? So just going back to our 1D example here, or 2D example, right? If I added this concept or subspace here, right, and I have another subspace in, I guess a 2D example is not really that good. So maybe I'll give you a 3D example. Let's say I had C1, right, and it has like these directions here, X and Y, right? And I have C2 and it has this direction here, Y and Z, right? So if I add C1 first, right, let's say I added C1 first, so then obviously C2, like Y is already in the span, right, of C1. So if I need to add C2, I'm just going to add Z instead. And I'm going to add like C2 as Z. And so that's kind of the orthogonal component, right? That's not in C1. And like you can think of that kind of as a rotation operation. You can think of it as a rotation operation. You're just kind of removing one dimension from the subspace. So, that's why they call it rotation. I thought it was a little confusing, but that's how I'm guessing it works. Okay, let's go into the experiments. Enough talking. So I thought it was really interesting that they said this. So the number of concepts was chosen such that the completeness measure reaches 0.5. And I thought 0.5 is like a pretty low amount of completeness. I mean, a lot of your W is still like unexplained, I feel like, with 0.5. So I thought it does not really result in a very complete explanation. So I was really curious why they chose 0.5. It seems quite arbitrary. Oops, where do I go? Over here. Okay. So I don't think we need to talk about relevance heat maps, activation heat maps. We already talked about all this. So yeah, okay. The only thing that really is, maybe I didn't drive across before, is that the concept activation maps are supposed to help you figure out what the concept actually means, right? Like in everything we talked about, we haven't talked about what these concepts actually represent or mean. And that's pretty challenging to figure out, like, in its own right. And so, but anyways, we'll get into that. So first, let's talk about faithfulness. Faithfulness is how well the model or the explanation represents the model's reasoning. And one way that people like to measure this is using this smallest destroying concepts benchmark. I don't personally like it, but it's okay. So basically, the idea is you remove concepts, right? And the most important concepts are going to have the largest drop. So you're going to get like some type of graph like this. Largest drop in the model is like confidence, right? So like this is the number of concepts removed, right? And this is like this is like the percent, right? Either it can be model accuracy or it can be model confidence, right, in the class. And the idea is like if it starts out really confident, and then you remove a concept, it's gonna like come down, and it's gonna keep coming down, right? And that's how you know you have like more of a faithful explanation, in the sense that like the important concepts are causing a big drop in the model. Now, the issue with all this is that it's like really unclear how you remove a concept from a model, right? So like if I have an image of a face, right, and I want to remove the face part, and like I just have like this now, and like let's just say like I made it all black, right? Let's just say I put the whole area as like a random color, right? Because I like blacked it out. It's like really unclear how the AI, like the machine learning model, should interpret this region, right? And so like it's I guess the whole point is just to say that we don't really know how to remove concepts. Like what does it mean for the concept to not be there, right? And there's been a lot of argument about this in the literature, but essentially the way the authors here get around it is they say that we're going to do some in-painting using like some type of imputation algorithm, which leads to comparably realistic images. And they say that thus the model is evaluated on manifold, right, in contrast to imputing with gray patches, as often done. I think that's a pretty unproven claim, and I don't know if it's fair to just say that. So, it's pretty hand-wavy. And, it's probably someone else could just stand up and say that, no, your model is still probably being evaluated off manifold. And, the reason that off manifold evaluations are really problematic, like, let's just say that, like, this is your model's manifold, right, like, on this region, and, like, you removed a concept from this image here, and it moved the image from here, like, all the way here, off the manifold. And, like, because you moved off manifold, now that's the reason that your model's accuracy dropped from here to all the way down here. Not because that concept was actually important, but just because you moved it off manifold, and like this is like a highly nonlinear region, right, of the network. It was never trained in this region, and so it just gives you some random response, and like, we just misinterpret it as to like thinking that, oh, the model actually really cares about that concept a lot. So, that's kind of the problem with this benchmark, and that's why I don't really like it. But it's fine. So anyways, here are the results. You can see this is the method that they propose. They have some variance over, I really hate that. They have some variance over here and here, and then these are two like industry, or I guess you could say other techniques. And like on the surface level, it seems like ICE is the best, right? Because it's like the most kind of like this. But they come up with some reason that their method here in blue is actually the best. I found it relatively unconvincing. Okay, this is their kind of argument. A meaningful concept discovery and quantification method should show a sharp decline. However, in principle, the sharpest decline is achievable via assigning the complete object to a single concept, because if you remove that object, then obviously, kind of like this green line, right? If you remove that object, then obviously your model is going to have like no accuracy, right? But that's kind of gaming the whole metric, right? And it's not really a useful explanation technique, is what they argue, right? And so that's why you want to show the strongest decline, but like not like basically not like super strong. Like you don't want it to be super strong, but you want it to be like kind of strong like this, right? Which is kind of like arbitrary, right? Like what if there was like what if there was like one in the middle, right? Where it was like a line right here, and then like a line right here, and then like right here. Like how would we say that like it's better or not, right? So like we're trying to use this metric, and then we're saying like, oh, actually these ones are not as good for like this and this reason. And I just think that it's all because this is not really a great way to actually evaluate faithfulness. But maybe that's just me rambling. So anyways, they use this to argue that theirs is actually the most faithful. And, I probably have some issues with them claiming that. I kind of sum it up here, arbitrary and unconvincing, but I think that's okay. Okay. Then they do some analysis to say like if their explanation is concise or not, right? So over here they have like they compare their different methods here, and then they have some metrics. So this is the mean dimensionality. Maybe I can write it. Maybe that'll be the most helpful. So this is dimensions, okay? This is the number of concepts. And then this is like how different the concepts are. So higher is better. Obviously you want concepts that are different. So they introduce some, way to measure how different the subspaces are. Not really relevant. But you can see like it's interesting, the mean size of the concept is 44, whereas like obviously in the previous works we just had one-dimensional concepts. So there's obviously a really big difference. And the number of concepts is actually really, really much less. Although if you kind of multiply these out, it's like roughly 160, you could say like roughly 160, which is kind of the same number here. So I thought that was interesting. Maybe it's kind of more. You could say this is actually like closer to 200, right, rather than 160. And then, they have some like, I don't know why, but they have some qualitative analysis here, which is, I guess, doesn't really feel super scientific, but that's fine. Yeah, so that's like their main evaluation, and let's look at the images, and we can look at the explanations, because we were all looking at math for now. So this is kind of the completeness aspect that I was talking about, where like each concept you can kind of figure out how much it contributes to the final logit score, right, of that class, which is really cool. But then you kind of look at the concepts themselves, and like the activation, remember, the activation tells you where, right? And then the local relevance tells you like kind of where it contributes. And this is local, so this is like for the specific image sample, right? And then global is like for the whole data set, right? So you can see like which concepts are most important globally, right? And then obviously in there you have the complement, right, which is like the orthogonal piece, which is interesting because it's like really, really important here. It's like a pretty high number. It's higher than any concept. And it's also interesting here, it's negative, right? So it's kind of weird, like how do you interpret that? And then you have the prototypes here. So like for that concept, what it typically looks like. And, I would say that some of these concepts are pretty difficult to interpret. Like this concept seemingly is the back of the car, right? Maybe I'll just put in highlighter. And this concept is also maybe seemingly the back of the car. Like there's some design here, right? It's like kind of unclear. Maybe it's also the tires. I don't know why the tires are being highlighted. Um, this concept seems to clearly be the tires. This one's a little easier to tell. But I think in general, if you're looking at these, it's a little difficult to tell what the concept actually is, which I think is one of the main drawbacks of this work. Is that we never talk about what the interpretability is of these concepts. So like that they have like some more qualitative examples. It's kind of the same thing. It's just kind of hard to identify what the concept is like it's just highlighting this region and this region. Like I don't know what that means. And like I just don't really understand what the concept is. I'm not sure the authors do either. And so that was my main kind of concern, is just the concepts are not very interpretable. It's a really interesting idea though, but it's just a shame that it's hard to interpret what these concepts actually mean, because it doesn't really, and they say it here, I think. So MCD prioritizes faithfulness over identifiability. And in this, and so they say we can guarantee to cover the original model reasoning structure, right? And like that's important. You have to be very faithful. However, this might obfuscate non-expert human users at first sight, since deep learning models will most likely not rely entirely on human-like features. And I think this is just them saying that, we know our explanations are not very interpretable, but it's likely that the model is not doing something very interpretable, which I guess you could say, but maybe kind of defeats the purpose of the explanation. And like, honestly, I guess I differ. I think that the models actually are doing something interpretable, and we just don't have the right tools yet to understand it. And so, anyways, that's my analysis plus opinions on the paper. And yeah, I think we can leave it there. Thanks for listening.